Okay, so this is on the second half of the algebraic tree diagrams little section, and it's on dependent algebraic tree diagrams. So dependent is where we generally the scenario is you take something out of a bag and you don't put it back in. So the second kind of probability depends on what happens in the first set. This is pretty hard. This is the hardest thing you'll do with tree diagrams. It's kind of the equivalent of the boss battle of probability. Considering GCSE, it's pretty hard. So let's just dive right into it. This is question 1 for you, but it's question 7 on the worksheet, just because there was the ones before, on independent. So again, let's just go through the question and kind of simplify it a little bit. So a bag contains 10 counters, so I'm going to say my total equals to 10. They're either blue or they're red. Counter is taken from the bag and not replaced. A second counter is taken at random. Probability that one of them is blue is 48 over 90. So I'm just going to call blue X, and then I can call red 10 minus X, because if we add these together we'll get to the total of 10. And then I can move from there. The reason why I chose blue as X is because kind of it came first in the question, and also they're asking for an answer kind of with blue in it. So I think if I leave blue as the simpler one, my algebra might not be as difficult to figure out during the question. It should work either way though. So probability that at least one of the counters is blue. So I might actually be contradicting what I was saying. It might have been simpler to have red as X, because it seems like if I'm having at least one counter is blue, that's actually kind of saying, well, I'm going to do 1 take away the probability of red, right? Because red is the only probability where there's not at least one blue counter, and then I want to take that away from 1. So I'm actually going to do that. I'm actually going to change that. And also they've asked us the actual question, how many are red? So as soon as we find X, we have our answer. So don't be afraid to kind of change your setting up once you've read the full question. So we're going to have blue, red, and we've already kind of mentioned our tactic. We could find these 3 and add them together, but that's a lot more work than finding this 1 and taking it away from 1. So, probability of red in the first instance is X over 10, because there's X amount of red counters and there's 10 in total. If we take a red one, we're going to have X minus 1 reds in the bag. And if we take one out of the bag, we'll have 9 total. The blue wouldn't change, the blue would stay as 10 minus X, but it would still be out of 9 because there would be 9 counters in the bag. We don't need that, I just did it to show you how the total of blues wouldn't change, but the total of the whole things would. So if we do X over 10 times by X minus 1 over 9, we get X squared minus X over 90. We know now that if we do kind of what I've mentioned out here, if we do 1 subtract X squared minus X over 90, that is going to equal to 48 over 90. So this is looking a bit horrible, but how else could I write 1 to help me out here? Well, I can write 1 as 90 over 90. And can you see how I've got a common denominator of 90 between all of this now? I can actually times this whole thing by 90 now, and what that's going to do is just get rid of these. So I've left myself with 90 minus X squared minus X equals 48. I'm then going to make it a positive X squared, so get my X squareds to this side of the equal sign, add my X, and I'm going to take away 90, so 48 take away 90 equals to minus 42. We're not just done yet though, we want to find out how many reds there are, so we need to solve this, I'm going to factorize. This is going to be, I'm going to have 6 and 7 in there, and I'm going to have minus 6 plus 7. So x equals to 6, x equals to minus 7. Well, I got 2 answers there. I can only have 1 correct answer for the amount of red counters. They can't be both 6 and minus 7. Which one makes most sense? Well, this one obviously makes no sense because we can't have minus 7 red counters. So actually we have 6 red counters. And you're going to come up with this quite a lot. You're going to have to decipher between situations, and it's not the most difficult skill, it's just we don't like negative ones. But quadratics do give negatives, and we can't help that. The quadratics does more than we need it to do, and we have to use our bit of intuition and brain power to realise what we're actually wanting from the quadratic. Okay, next question, question 8. Bowl contains n pieces of fruit, so total equals to n. Of these, there's oranges and apples. There are 4 oranges and the rest apples, so 4 plus something gives me n. So n subtract 4. If we add them two together, they get me n. Or you do the total, take away oranges. 2 pieces of fruit are going to be taken at random from the bowl. The probability that the bowl will then contain n minus 6 apples is a third. This is a weird one because it's not obvious what path. They're not saying like take 2 apples or take 2 oranges or at least 1 apple. You really need to think, well, if I take an apple, then I'm still going to have 4 oranges, aren't I? But then I'm going to have n minus 5 apples. And then if I take an apple again, so this is take 1 and this is take 2, I'm still going to have 4 oranges, I'm not taking any. Then I'm going to have n minus 6 apples. So what they're actually asking us is take 2 apples. It's basically what they're saying in a really complicated, horrible way. But that's how they make these questions harder. So basically we're asked the question of what is the probability. The probability of taking 2 apples is a third. So let's go ahead and do that. We'll do oranges and apples. Oranges is 4 out of n, because 4 oranges and n is the total. And this is n minus 4 over n. We don't actually care about this path, do we? And we don't actually care about that path on top. We only care about 2 apples. So if I take an apple, we'll have n minus 5 apples. And if I take any of the fruits, I'll have n minus 1 lots of fruit in the bowl. So the probability of this will be n minus 4 over n times by n minus 5 over n minus 1. And that is going to equal a third. So we've got our double bracket expansion here. Always take this slower if you need to. I'm just going to jump straight into it. So n squared minus 9n plus 20. I can do that fast because I know that it's kind of these added together and then these times together. It's the inverse of factorizing, isn't it? And then we've got n squared minus n equals a third. Cross multiply. So this is going to be 3n squared minus 27n plus 60 equals to n squared minus n. Take my n squared to the other side. 2n squared, add my n to the other side, plus 28n plus 60. I can divide this all by 2, so n squared plus 14n plus 30. And then I'm going to go into this corner here to finish it off. So I need to factorize and solve. So factorizing this, it's going to be... Oh, actually, I made a mistake here, didn't I? Adding this on. No? Why have I... This should be minus 26, shouldn't it? Bloody hell, I'm stupid. I don't even know how I got that. So then this should be minus 13n. Sorry about that. So then the factorizing actually works. That's why I was a bit stumped. We're going to have minus 3 minus 10. So n equals to 3, n equals to 10. They're both positive, so how do we know which one is wrong? Well, we have n minus 5 apples. So if we have 3 minus 5 apples, doesn't work, because if we consider that apples, 3 minus 5 equals to minus 2, and that makes no sense. And then if we consider that one, 10 minus 5, then yes, I should probably say, well, consider the original, right? Yep. So there we go. Find the value of n. The real value of n is 10. You won't get all your marks if you leave 2 answers at the end. You'll get 5. That extra 6th mark is for this kind of reasoning. So it's not always just because they're negative, it's sometimes they're, when you substitute it back into your equations you've made, or your expressions you've made, you do get some negatives, and they make no sense. Okay? Question 9. There are some red counters and some white counters in a bag. At the start, 7 of the counters are red, and the rest of the counters are yx. So the total is x plus 7. Alfie takes at random a counter, so we've got Alfie, and then he does not put it back in the bag, and then he takes it again. So actually I'm not even going to bother writing Alfie. I thought there was going to be 2 different names. I'm just going to write take 1 and take 2. So again, this is another show that I'm not even taking care, not even taking notice of that. I'm just going to magically appear at that after I've done a load of working. And that's meant to say minus. Probability that the first counter Alfie takes is white, and the second counter, so the probability of white, red, equals 21 over 18. That's basically what that is saying. So let's go ahead and find that. Red, white. We don't actually care about that, do we? Because we want white, red. Red, white. We don't care about this because we want white, red. So I'm not even going to fill that in because we don't need to. So x over x plus 7. And if I take a white one, it will affect the total, but it won't affect the amount of red ones in there. It will only affect the amount of red ones if I go on this top path and start taking reds in the first column. It would affect this. This one down here would be x minus 1 over x plus 6, but we don't need that. So this is x over x plus 7 times by 7 over x plus 6, and that equals to 21 over 80. So again, let's sort this left side out. 7x over x squared plus 13x plus 42 equals to 21 over 80. So I'm going to cross multiply. So 80 times by 7, which is 560, x, 21x squared. So already looking at where I want to finish, I feel like I'm going to be dividing by 7 in a little bit. 21 times by 13, which is 273, and then 42 times by 21, which is 881. I am going to take away the 560x to the other side. So 273 take away 560. That's minus 287x. So I know I want to get from 21x squared to 3x squared, so it's a logical step here to divide by 7. It's always the key, kind of look at your highest power and think, how can I get from that to that? And if your other numbers work out, then you've obviously done it right. Yep, that works for me. So 287 divided by 7 is 41, and 881 divided by 7 is not quite what I want it to be. Let me double check my working on this. 6 times by 7, as though I got that right, yep. And then 42 times by 21, 882. So 882 divided by 7 is 126. Spot on. I've answered that question. We could go ahead and solve it if we went on to the extensions of factorizing and stuff like this, but we don't need to for this question. How many more are there? Just 2. Okay. You can just skip through this as fast as you want to anyway. Bag contains X counters, so total equals to X. 7 of them are blue. What's the other colour? Not blue. Equals to X minus 7. The total minus how many that are blue. So this is kind of a part A, B. We want to show this, and then hence we want to do that. So this might be split into 2 questions on an exam, A and B. Some takes blah blah blah. Probability that they both take a blue counter, so probability blue equals, I don't like decimals, I like fractions, so a fifth. So let's draw our tree. We're going to have blue, and B dash means not blue. 7 out of X. We only care about if they're both blue, so we don't care about this path down here. We actually only care about this path that I haven't crossed through. So if I take a blue, there's going to be 6 blues left, and there's going to be X minus 1 total. So that's meant to be an arrow. So 7 over X times by 6 over X minus 1, that equals to a fifth. So 42 over X squared minus X equals to a fifth. Cross multiply. We seem to get this in all of these questions. So 42 times 5 is 210. That equals to X squared minus X. So X squared minus X minus 210 equals to 0. Spot on. That was a nicer one compared to the others. And hence solve. So factorizing when we solve it is going to give us a nice whole number answer, and we'd always expect a whole number answer when we're talking about counters in a bag. You can't have 7.32 counters in a bag, can you? So factorizing is always the way to go with these. Have a little think. I think 14 and 15 are going to work for this, because obviously they're numbers that will make to the minus 1, and they times together to make 210. I need my larger number to be minus, because that's how that's going to make that a minus 1. So I've got X equals to minus 14, X equals to 15. Well, we can't have this one. Always give a sentence as well. Just leaving it out doesn't show your understanding of why you're leaving it out. So you just need to do a simple thing saying we can't have that. We can't have a negative amount of counters. So 15 counters in the bag. Easy peasy. And then the final question. Huzzah. There are only green pens and blue pens in a box. So we've got green, blue, and we've got total. I always like doing this, because that means I never have to look at the question ever again. I can just look at my simplified version of the question. There are 3 more blue pens than green pens in the box, and there are more than 12 pens in the box. That's a bit of a vague sort of thing to say, but I assume when we go ahead and solve a quadratic, we might get 2 answers, one less than 12 and one bigger than 12, and that'll help us decipher between our quadratic solutions. Anyway, let's go on to this. So there are 3 more blue pens than green pens. So if we say green is X and blue is X plus 3, the total is going to be 2X plus 3, isn't it? So we've already figured them 3 out nice and easy. Probability that Simon will take 2 pens of the same colour, so that's probability of green, green, and the probability of blue, blue. and that equals to 27 over 55. So it seems like we're going to need to draw our full tree for this one, which I do not like. But let's go ahead. So green, blue, green, blue, green, blue. I'm going to get a different colour to draw these on, because if I'm drawing a lot on it might get a bit messy. So the probability of green is green over the total. Probability of blue is blue over the total. If I've taken a green one, then I now have x minus 1 greens. If I've taken a counter out, I'm going to have 2x plus 2. If I've taken a green, blue hasn't changed, so that's still going to be x plus 3, but the total will drop by 1. That's meant to be an x plus. No, I don't like that. Looks like a 4. And if I've taken a blue one, the amount of greens hasn't changed, so that will stay as x, but the total will have changed. Notice the total is just always the same on all of these, so once you've figured it out once, it's quite simple, the denominator. And if I take a blue, well then the blue has decreased by 1. The paths I want are these two, aren't they? I don't want them to. I mean, you could do them two and take away from 1, but what's the point? I'm going to find out this one first. So x over 2x plus 3 times by x minus 1, 2x plus 2. And then this one here would be x plus 3 over 2x plus 3 times by x plus 2 over 2x plus 2. Notice how these will end up having the same denominator. So you'd only have to really figure out these multiplication once. X squared minus x over 4x squared. I'm going to do this one in a grid actually. Four x squared, 6x, 4x, so that's plus 10x, and then plus 6. This one is going to be x squared plus 5x plus 6 over the same thing as what I just found up there. And then I need to add these two, and that is going to make up my 27 over 55. So see if I can, am I going to be able to fit it on? Alright, I'm going to run a bit of magic. Where's he gone? Oh, this is a nightmare. Here he is. Skip past this, please. Okay, I've given myself a little bit more room, and I've just covered up my old stuff up there, which we don't need. Okay, we're back in. So they're my two things that I need to add together for this. I'm going to go into red now. So x squared minus x plus x squared plus 5x plus 6 all over. I've skipped that step of joining the denominators. And that equals to 27 over 55. Let's clean up this top line. We'll have 2x squared plus 4x plus 6. I can divide top and bottom by 2 on this fraction, so I am actually going to do that because it'll make it just that bit easier to do my cross multiplying. So x squared plus 2x plus 3 all over 2x squared plus 5x plus 3. And this is meant to be 55. Okay, so time to cross multiply. This is going to be, I'm going to times by 55 on this side, 55x squared plus 110x plus 165 equals to 54. So we can see 54 and 55, that's going to give us a nice single x squared, so it's working out relatively nicely so far. Plus 135x, and then 3 times 27, plus 81. I was meant to say 81 and my words chopped it. Plus 81. I'm going to go over, actually I can do one more line below. So let's tidy this up. We're going to get x squared, 110 take away 135, minus 25x, and then 165 take away 81, plus 84. Ugh, this looks disgusting. Let's have a quick think. Let's just trial and error some divisions by 84. Can we do 16? No. Can we do 14? 14 and 6? Nope. Can we do that? Nope. Can we do... See if you can beat me to it. I've done this before, but I don't have it in front of me. And I'm just double checking I haven't done anything wrong. Don't think so. Okay, see if you can beat me to it. This is the hard factorization. I'm doing the cheating method a little bit, just to beat you. So we've got 21 and 4. How's that? Easy peasy. (21 and 4), and we want both negatives. So we would then get x equals to 21, x equals to 4. Let's go back to see where that it said something about being more than 12. There are more than 12 pens in the box. So the total is 2x plus 3. So if we did 2 times 4 plus 3, that would give us a total of 11, which we know there's more than 12. And this one would give us a total of 42, 45. So we like that one. So the value, work out the number of green pens in the box. Well, green pens is just x, so there is 21 green pens. Alright, that was a long one. Hopefully you got something good out of it and you were just able to skip through to find kind of the stuff that you specifically wanted to see. Alright, cheers.